physics be emergent? And obviously I tried to convince you that the answer could possibly be yes, in some sense. But before going there, I also thought I'd give you a little bit of intro, one slide. Since I'm talking to some philosophers, I need at least one quotation. So here's a quotation by Martin Gardner in this book here, and I actually found this quotation in one of your papers, Chris. So he said, the hypothesis that there is an external world not dependent on human minds, made of something, is so obviously useful and so strongly confirmed by experience that we can say without exaggeration that it's better confirmed than any other empirical hypothesis. And then he says, so useful is the posit that it's almost impossible for anyone except a madman or a professional metaphysician, which I'm not, to comprehend a reason for doubting it. Now the message of this talk now is, we can, and maybe we should, we can actually consistently be the madman. And maybe this will help with some important open challenges that we have in physics and around physics. Now, what I'm doing here is I try to give you a kind of toy model, if you want, theory that's meant to be a proof of principle that shows that in principle that could work, but I'm not claiming this is exactly how the world is, even though maybe it could to some extent. Yeah. I'm also emphasizing that I'm really focusing here on like building this kind of model, just making it work, and not so much on its interpretation. There will be a probability. You might discuss what that probability means. I'm not discussing it a lot here. There's also relations to what many philosophers said before, for example, Carnap and many other people. I don't know much about philosophy, and that's why I'm also excited to work with Michael Caffaro now, who's also sitting here, on exploring a bit more which of these ideas have been come up before, how it relates to certain ways of thinking, like, for example, Carnap's Aufbau. But here it will be more on the kind of really constructing this model side in this talk. So here's an outline of the talk. First will be a motivation from the perspective of a physicist. Why should we ask this question? Then I will give you the postulates of a kind of theory or a very simple toy model. And once we have that, we may ask, well, if we start with a first-person perspective, what about the rest of physics? And the third part will try to show you that we actually get some aspects of physics as we know that as a consequence for free. The fourth part will really be just 2 slides with some new predictions that you would get if you take that seriously here. And they're pretty surprising and pretty wild, and that's also why I don't want to spend too much time on the fourth part. Okay, so what about motivation? Why should we look at a question like this? About the first-person perspective? So my personal question that I found interesting to starting this was just maybe some kind of philosophical question to ask, why is there a world with laws of nature at all in the first place? And in particular, why are these laws of nature computable, probabilistic, and algorithmically simple? So what I mean is that we can basically write down the equations of physics and the laws of physics as we know on a piece of paper. We can program them in a computer and make the computer make the predictions for us algorithmically. Why is that working? That seems very, very remarkable. Now you may say these are not good physics questions. You shouldn't really ask them as a physicist, but there are actual physics questions that I want to argue are related somehow to this. We all know the puzzles of quantum theory, but we shouldn't only focus on that, I would say, because there are other fields where people have also conceptual puzzles that I claim are related, for example, in cosmology. Where people talk about things like the Boltzmann brain problem that I will mention in more detail soon, or the measure problem, or they'll ask why do we have low entropic initial conditions in our universe. And there are these other questions which sound a bit like science fiction but may at some point not be, like what if we at some point simulate a brain on a computer, and all kinds of thought experiment that philosophers really talk about in that context, which is related obviously to the philosophy of mind, where I also don't know much about. But you can really see that this is conceptually related. Now, my claim is not that we can solve all these questions somehow, but my claim is that there is a common core to all of these questions. So all of these have something in common, and it has to do with the probability that an observer from his first-person perspective would assign to his future observations given what he remembers from the past. That's common to all of them. And to illustrate, let me just give you 2 examples in like this cosmology and future technology example. So here's some conditional probability that arises in cosmology. So cosmologists discuss the following. They discuss Boltzmann brains. So these are, I guess most of you have seen that, but the argumentation here is somehow that if you have a really big universe governed by thermodynamics and quantum theory, then you have random processes happening out there, like particles being created and then annihilated again. And then sometimes very, very unlikely processes happen if the universe is big enough, like a brain pops up. With all the memories that we think we have now, just randomly popping up as well there. I mean, probability is not zero, so make the universe big enough and it will happen many times. And then, suddenly this brain will be there and then think, and well, things are suddenly strange, what's going on, and then disappear, something like that. And people write the PhD about that. So here's like the idea that string theory might help to resolve the Boltzmann brains. When you build a model, you say if the universe has a finite lifespan, that will deny Boltzmann brains the time they need to outnumber us. Now here's the argumentation in a nutshell. What you do is you want to fix some cosmological model X, which just predicts a very large universe. And then what you do is you try to count how many Boltzmann brains would you expect to appear there statistically, like the number of Boltzmann brains. And you say how many naturally evolved brains would I expect to appear there. And if you say, well, if there are much more Boltzmann brains than naturally appearing brains, then something's wrong. And they would say, I would conclude that as an observer, my probability of having all my completely natural and normal past observations, given that, about the future, is just dominated by these strange Boltzmann brain experiences. Where you'd say, now I'm standing here, but in a second from now I'm thinking, what the fuck, I'm suddenly in space. And then, So this is not what we see. I will still have a coffee, hopefully, in an hour from now. So this falsifies model X. Now, I would say there's something that we fundamentally don't understand there. So this is not really, we don't really know what's going on when we try to make this argument. Now, future technology. Here's a book that Nick Bostrom has written on superintelligence, and he argues against the dangers of artificial intelligence. And here's a thought experiment that he made. He said, well, maybe one day we want to program an artificial intelligence to solve our problems when we ask it questions. And maybe we tell the artificial intelligence, hey, please develop a medication for disease X. And then the AI is very clever and just goes ahead and in its memory just simulates a couple of humans, trillions of them, and does a lot of horrible medication tests to them, and then returns the result and gives us the medication. Now, that would be maybe very bad. So you can ask the question, what does that mean? Are these, and that's what he writes here, are these simulated humans conscious and alive? And maybe you can see the conceptual similarity between the trillions of simulated brains that Bostrom talks about and the Boltzmann brains that the cosmologists are talking about. Because also in this case, you can ask about this conditional probability. Suppose I run a simulation of some existing observer like myself and do all these horrible tests. Would this really increase the conditional probability of future suffering given my past observations, yes or no? And I would argue that we don't have the slightest idea how to approach questions like that, at least from a physics point of view. Now what do we make of that? I think what it motivates is to look at these conditional probabilities here and maybe start with them. So an approach would be to say, let's start by just dropping any assumption of an external world. Let's get rid of this assumption. And let's instead start with conditional probabilities of this form. First-person conditional probabilities of past observation given future observations for every single observer privately. And how do we do that? Well, basically, let's just postulate this distribution. Let's say, here's a toy model, here's a theory, and that's the distribution. Now let's see what's happening. And you want to postulate this distribution by making a well-motivated guess, and in the end check if that's consistent with the physics as we know it. So how would you do that? And now that's the second part of my talk. And here's a sketch how to think about that. Here we have an observer. It's a guinea pig. When I put a human, then people tend to get angry, so I put a guinea pig here. And the idea is that at some point in time, I call her Abby in the following, it doesn't really matter, but she will have something that she sees and knows and remembers, basically the content of her brain. And you can imagine encoding that into some long sequence of zeros and ones. It raises all kinds of questions, I come back to them later on. Okay, maybe a moment later on she sees and remembers something else, maybe the street and the mountains, and then this corresponds to another description of her memory state. And then something else, maybe she sees this wall, and then looks behind the wall. And at this point, she doesn't really know what's going on when she looks behind the wall and what she sees next. So maybe she's just seeing that there's a kind of a garden there. Or a priori, she could have a very strange experience. When she goes behind the wall, she's suddenly in space, like in this Boltzmann brain problem. And now what we do here is we say, well, that's somehow the situation more or less. So we have an observer A, and its experience or its states or its observations, I use these three things interchangeably, and I do not want to fix a fixed interpretation right now. Whatever that thing is here, they are given by just binary strings of zeros and ones, of a sequence of them. And you just see what's the probability of the next observation. Well, it's a conditional probability, and that one is just conditional algorithmic probability. That's a postulate. That's it. So this is like a toy model or a theory. I do not make any other assumptions, just that. So it's very simple. And yeah, to start with here, I assume that observations are fundamentally discrete. So I can, in principle, think of encoding them into binary strings like this one. Now we could talk about maybe, why we should do that, or maybe we should not do that, but technically we will need it, and I think there are also some arguments to be made why that makes sense, but I don't have time to really talk about that. What you can say, interestingly, is you can say, well, an experience is not a string, so how do I encode an experience into a string? But you should think of these strings as something like coordinates in physics, where also like you have something like a space-time point, you don't really know what it is, but you can encode it into coordinates, and the choice of encoding doesn't really matter. Something like that will happen here as well. So what I will now discuss is what this algorithmic probability is, and actually why I chose it here in this postulate. So what is algorithmic probability? The idea is that you start with a computational model, for example, a Turing machine, a universal Turing machine, and it's a monotone one. So what does it mean? It means it has an input tape and an output tape. And what it does is it reads one bit after the other. It reads the first bit, then the second, then the third, and so on. So the tape can only move leftwards, if you want. And it also writes the first bit, then writes the second bit, and so on. That's what monotone means. And now you can ask, what's the probability that this machine outputs something here that starts with a string x, like maybe with 0011, if the input bits here are chosen by a fair coin toss? You just choose them randomly and look at the outputs. And you call that probability mu of x. Now, formally, you would write it in that way. You look at all the programs that you feed into the machine, which give you something, maybe this x, and then maybe something else afterwards. And that's your probability. So here I would say maybe I have this output here, and I got it from this input. So I have in the sum 2 to the minus the length of this input here, which would be 1/2 times 1/2 is 1/4, and then some other term. So you get some number, which is the probability of that string. Bad news is that this number is not computable. It's just enumerable, which means you can estimate it from below somehow. It's also not really a probability distribution. So if you ask, what's the probability that I get something that starts with x? You would ask, well, it should be the sum of getting something that starts with x and then a 0, or something that I get x and then a 1. But it's actually less than or equal to that. So it's a semi-measure, not really a measure. But then you can normalize it and you get a probability measure. And that's algorithmic probability. Okay, and the interesting part, of, like most interesting aspect of it is that it somehow formalizes Occam's razor in some sense. Namely, this distribution has large values for simple strings x. So you can say the probability is larger than 2 to the minus the complexity, Kolmogorov complexity of x. So this is the length of the shortest program for x. So if I have a string that has a short description, it will have high probability, like the first million digits of pi. But otherwise it will have small probability. Okay. Now we need a little modification here, because we don't want sequences of bits, but sequences of strings. Remember this observer, and there's a string, another string, and so on. So the modification is then just that the outputs are now not bits, but strings, written one after the other. you do the same definitions and you get analogously a notion of algorithmic probability. And that's the one I'm talking about here. So this is the one that actually appears here. And this is a conditional version of that probability, which is just the usual formula from conditional probabilities. Now, what's this A here in my notation? For the sake of this talk, this is really just labeling the observer, like Abby. A is now the observer that I'm interested in. It doesn't say much more. But I'm dropping here some details, but let's keep it like that for now. Now, you may ask, well, but doesn't the theory then depend on the choice of universal machine? What if I choose another universal machine? I get different probabilities. And the answer will be no, in fact, but no for very non-trivial reasons. So you can say that the theory that you actually get as a result of this will be independent of the choice of u. This took me really a while to think about that, because people in artificial intelligence think about that also. So if you're interested, I can talk about that later a bit more, but let me go on here now. So this is now, so here's just to finish this. Here's an open problem, just to mention it for later. So if you think of that thing now, you know, Abby is here and she wants to guess, am I going here or am I going there? Then you would want is that actually this probability, the conditional probability, depends only on what she knows now. That's if you're a Bayesian, you might want to say that. But here, it depends on all her past, on all the past observations. So like conceptually, it would be somehow cleaner if it depended only on the current or last experience observational state. But the problem is I don't know how to formulate the theory in a meaningful way if I want that. So it's just mathematically challenging and I don't know how to do it. But I conjecture that it can be done. It's called this Markovianity conjecture, and I come back to that later. It doesn't matter much for now, but it will become interesting later. Okay, so why algorithmic probability? I mean, why is that the P that I put here? And can give three reasons, but let me just give you one reason. And that's, I would say, what we have here can be seen as an extrapolation of Solomonov induction. So that's Ray J. Solomonov, and he came up with this method of inductive inference. And here's basically the method. It's very simple. So Solomonov said, if you are an agent in some probabilistic environment, you don't know the probabilities, but you just make some observations. You see one bit, then the next bit, and so on. And you want to predict what bit you see in the future. Then you should predict the next bit just with conditional algorithmic probability. That's his prescription. Doing that is called Solomonov induction. And what he proved is that this works in a nice sense, namely in all computable probabilistic environments, this somehow converges to the correct probability and does so pretty quickly. And that's why people write books about this, like Hutter, a book on universal artificial intelligence, where they really try to use algorithmic probability to program a machine that predicts the future in some sense. Okay, now what does it mean for us? Well, as far as we know, our current physical theories, as we know them, are computable in some sense. Namely, if we describe an experiment and feed it into a machine, then this machine or algorithm can compute the output statistics that we should expect. Now that's good enough for Solomonov induction to work under that circumstances. So that's enough to guarantee that Solomonov induction will in fact, assign the same probabilities for future outcomes that we would do. So Solomonov induction will do at least as good as our best physical theories in prediction, in principle, if we could implement it, asymptotically after like many observations. So what does it tell us? Well, in a way it tells us that this method just agrees with our physical theories in the regime where we can apply our physical theories. Now we have these other strange situations like Boltzmann brains where we don't know what physics is telling us. So then why not just apply Solomonov induction there? Let's just extrapolate this method to these kind of new regimes of experience where we don't know how to apply standard physics. And that motivates, if you go back just this postulate, they say, think of the chance of the next observation y in terms of conditional algorithmic probability. Good. So for the Bayesians here, you can interpret this probability in many different ways, if you like. For the rest of the talk, I would say let's interpret this as some kind of objective chance. So after seeing this, there's a certain chance of seeing y next, which is given to the observer, which is given by conditional algorithmic probability. Is not the only possible way to interpret this. Okay. So there are also other reasons, like structural motivations, why you might want to consider algorithmic probability, but let me not discuss this just to save a bit of time. And let's look at the third part, where we can just ask, well, if we have now this thing, what would it mean? If you're an observer like that, what would the world look like for you? I mean, the world doesn't even make sense there yet, because I'm only talking about experiences, observations of an observer. There's no mention of a world. So what about an external world? What about other observers and so on? Now let's see. Let's see what predictions we can extract from that. Now here's the first prediction that I called the principle of persistent regularities. And the idea is the following. Here's your observer, and she has, made at some point her observations are described by some binary string. Then she's observed something else, something else, something else. And then she wants to predict the future. And maybe she's interested in a particular property, which we formalize by a test. So a test, a computable test, is just a function where you feed in some bit string and you get yes or no as an answer. For example, you can ask, does the string start with a 1? And then you see here the answer would be yes, here the answer would be yes, and the answer was yes all along in the past. And now suppose this is the case, the answer was yes over all of the past. Then you prove the following, theorem. You can prove that with high probability, probably close to 1, the answer will also be yes in the future. So whatever regularity you discovered in the past will tend to persist in the future as long as it's a computable regularity. The intuitive reason for that is that algorithmic probability favors compressibility. And this kind of thing makes the whole sequence just more compressible. That's why you get such a thing. Here would be a way to formulate it as a theorem. I don't want to go into detail, but you kind of say that like if you have n times seen a yes, the probability of seeing yes again is very close to 1. It's larger than 1 minus 1 over n for all but finitely many n. So you can make statements like this. Good. Now, I would claim this is basically enough to exercise Boltzmann brains and get rid of the Boltzmann brain problem. Well, now let's fix a computable test. And the computable test just asks whether an observation that Abby makes, these observations are typical for a planet-like environment. You think of writing a computer program that kind of tests for this and gives you yes or no as an answer. And suppose the answer was yes in all of the past, like it would be for us now. Well, then the theorem will tell you that it's probably yes also in the future. So it's a very strange experience that I've described before of the Boltzmann brain. It's just highly unlikely, because it would not be typical for a planet-like environment. So you'll not have that experience, or it'll have very small probability. Okay, just look at the time. Good. Good. Now you can actually say more. So here's something. Another prediction is that in the long run you will see something like simple computable probabilistic laws. So what you can prove as a theorem is that this algorithmic probability, after making many observations, will converge to something simple and computable. And this will happen with a probability which is at least 2 to the minus the complexity of this distribution. And the Kolmogorov complexity of this distribution is just the length of the shortest program that makes the universal machine generate this distribution. So for a fair coin toss, that would be a very small number here. Yeah? But for a very complicated setup that gives you probabilities that would be very large. So what does it tell you? It tells you this irregular, non-computable beast P, this algorithmic probability, converges to something nice and computable in the long run. And it is random which measure we obtain, because this happens with some probability to get the measure mu. But simple measures are preferred, because what a simple means it has a short description, means that the Kolmogorov complexity is small, being that the probability is large. And that would tell you that observers in the long run see simple computable probabilistic laws, if you want to call them, but the exact form of them is contingent. Now, this is still operating on the level of experiences. So that's what the observer experiences and so on, and that's the probability of the next experience given the previous ones. It still doesn't talk about an external world. So what about an external world? Well, we get this in some sense. So we have to just look at the theorem and tell what does it tell us. So what does it mean that k of mu is small? It means that you have this universal machine with a short program generate that measure. So here's your machine, and what you have is if you feed random inputs into the machine, it will produce outputs which are distributed according to this mu, this distribution mu. And so you have a simple computation which just sequentially generates this outputs that are distributed according to this measure. Now you shouldn't really think too naively of this machine with its tapes and with its memory, because all that mathematically goes in here is that this is a computable function. So it's an abstract computational process. So think of it more in an abstract form. You have a process that just generates these outputs that correspond to the experiences of the observer. And obviously, all that the observer sees are these observations and not the process. Yeah? That's so this process here is not directly subject to experience, but since it generates these experiences, it's somehow correlated with future observations. And I would claim that this is what we call an external world. So for example, I don't know what's behind this door. Maybe somebody just took away all the coffee, which would be really terrible in half an hour from now. Yeah? I mean, it's not part of my experience now, but it's correlated to what I experience later on. And it's part of this external world over there. And here would have the same thing. So you might just want to call this computational process, which exists here and generates your experiences as an external world. Good. So somehow we obtain an emergent notion of external world in some sense. And this world is somehow not fundamental. It's more an ontological model. It's somehow a convenient illusion that the observer can use to predict the future. And what's it like? Well, we don't know. We just know it's typically simple, computable, and probabilistic, but its detailed form is contingent. But now, there are some generic features of simple computational processes, like the cellular automaton that starts here and then spreads out as time passes, namely that they start in some simple initial state. And as far as we know about physics, this seems to be compatible with what we see in physics, because cosmologists talk about low entropic initial conditions that they see in the past. So that seems to fit roughly to some features of what we see. Okay, now this is maybe the most interesting part in the context of this conference, because it gives you a mechanism which shows how there can be an emergent notion of objective reality if you have more than one observer. So think of two of these observers. I've called them one A and B, Abby and Bambi. Now they all make their own private observations. They are not embedded in any world or anything. I mean, according to the postulate that I've shown you, they make future observations according to some conditioning on their past observations, and that's independent from each other. And according to the theorem that I've just shown you, they will kind of, see something like an external world around them. So maybe A finds herself in some computational world where you have to run around and jump and collect points, like in this one. Or maybe B has something else. But now suppose something happens, namely A sees something in her external world that seems like another observer B to her. Like I see Julio over there. It looks pretty much like an observer to me. So what does it mean? Well, look at A world alone. And in A world, Abby sees this other thing here, which seems to, process some information and just looks like another observer. You can ask, but does what A really sees really correspond to the first-person perspective of another observer? So what do you formulate that? You formalize it by saying you have this computational process, you have another function, a computable function that reads out in every time step some string, which you just interpret as a string of content of experience of another observer. And then you can compare two probability distributions. One distribution asks, in this world, within this probabilistic process, what's the probability of getting some of these experiences here? What's the probability that B sees x1 and then x2 and then xn? Yeah, so that's basically asking in this picture, like in this world, what's the probability of these observations here? And then there's, according to the postulate I've shown you, there's algorithmic probability, which is the thing that's really important for B. Subjectively, B's experiences will be described by algorithmic probability. And they are different a priori. They have nothing to do with each other. We can ask, are they really different or are they the same? So let's look at like a colorful example. So suppose we're in A world, and Abby in her world every day sees the sun rise. Every morning she will see with probability 1 the sun rising. And now you can ask, well, obviously, if she sees the sun rise, Abby also sees that Bambi sees the sun rising. Okay? It's a bit arguing like Renato in his talk now about an observer observing another observer. Another question is the following. If Abby has a chance of about 100% of seeing Bambi see the sun rise tomorrow, then will Bambi have a chance subjectively from her first-person perspective to see the sun rise tomorrow, which is the same. And you would say that in the first part, this is what I call the distribution nu. The second thing, is the first-person perspective is governed by algorithmic probability according to the postulate that I've shown you. And so what's the answer? Well, the answer is yes, asymptotically. So you can prove a theorem, namely with probability 1, after making lots of observations, these two distributions converge to each other. So the difference between the two goes to 0. So after making lots and lots of observations, yes, Bambi will actually also assign probability 1 of seeing the sun rise tomorrow. And this is basically just a statement of Solomonov induction. So for the same reason that these machine learning algorithms work that use Solomonov induction, it's also the reason why you have this convergence here and why these two observers will in the long run actually agree on what probabilities they assign in the future. Good. Right. Now, not sure how much time I should spend on that. I haven't talked about quantum theory at all at the moment. And I want to say a few things why quantum theory fits in the picture. It's at least not in contradiction with what I've shown you. So maybe one slide which should convince you that what I've shown you is largely conceptually compatible with quantum theory. So according to this toy model, all there is, in some sense, fundamentally, are experiences and probabilities of future experiences. And so if you take that seriously, then you shouldn't be surprised that observers, in whatever they call their world, see worlds that are described by theories of the quantum kind, in some sense, where measurements or experiences play some kind of distinguished role or some primitive role. So in this sense, I think this worldview shares some elements with Cubism. Though many things are different, obviously. And also you would say Wigner's friend type thought experiments are not really worrisome for such a worldview. Here's the setup that Renato has shown us, because what I've shown you says that different observers' observations are not in general consistent. They just are under some conditions. And so you could look at Renato's talk, but also I will talk about some fun notion called probabilistic zombies in the last part of the talk, if I still have a bit of time. Yeah, so these are things, I guess, that fit some of the conceptual messages that we've learned from quantum theory. Now you can say a bit more, and I'm not sure how much time I will spend on that because it's not really the focus of the talk. So what about all these other actually interesting quantum effects that we know about our world? Do they have a place inside a worldview like this? And here's a way how they would fit. Yeah? I'm not claiming that this is like where they really come from, but at least it's consistent. Okay, so here's what I've shown you. I've shown you that after a while, observers will, see a computational world that describes how their observations are distributed. And there's a problem, namely all the agent at some moment really currently knows is his current state xn, the last one, and not all the previous observations that he made. He may have forgotten what he's seen before, or what she's seen before. So then the problem is that the agent cannot really use this to predict the future. So what you want to is you want a distribution that really allows you in a Bayesian way to predict the future. So you say, well, let's just have a measure that has a notion that's called predictive if it allows me to predict the future. Basically, if it induces a conditional probability distribution of the future given the present, if that's possible in all cases. And some I would say this is what David Lewis would call the principle, namely that your subjective degrees of belief, like betting on the future given what you know now, should be determined by objective chances, which in this theory would be those guys, if that's possible. And now let's make the assumption that this is the case. Now, if you think back of this open problem that I called you, where I can formulate the theory in a Markovian way, you wouldn't have to make the assumption because that would just be a Markovian distribution to start with, so it would be automatically satisfied. Okay. So if you have a Markovian distribution, for example, then it's predictive, because what you see next depends only on your current state and not on the past. But also, if you have situations that are not Markovian, but where you're forbidden to go back to a previous state, then you can also predict the future. Let me just drop that or skip that a bit. But a loop means that as an observer, you're in this state and that state, and you go back to your old state. And this has some very interesting effects. And that happens, for example, in the Sleeping Beauty problem. And some of you have seen that. Let me maybe not read this, but to save time, just give you a picture. That's a Sleeping Beauty problem. Here's Sleeping Beauty. She's part of an experiment. There's another experimenter out there that didn't draw, maybe call him Wigner. And what Wigner does is puts her Sleeping Beauty to sleep and then wakes her up. You know? And then maybe puts her back to sleep, gives her a drug so that she doesn't remember whether she has been awake and just gets put to sleep again. And maybe by a coin toss, he decides whether he does it once or twice or maybe more than 2 times. And since she always forgets that she'd been waken up, her memory and everything she knows just goes back to the old state. At some point, the experiment ends, and then maybe she says, oh, I got enough of this princess stuff. I do some serious work now. And that's the other state. So this is now a history that she sleep, awake, and so on. And then at some point, this ends. And whenever she's awake, she can ask, how many times have I been awake now? 5 times, 7 times? I don't know. And that's a random variable that I call hash here. And what you can show first is that if you have this predictivity, so if you want her to be able to predict the future even though she's forgetting the past, then this amounts to some conditional independence relation, namely nothing that she learns later on teaches her anything about how often she looped. So if she goes to work and asks her colleagues, hey, you've seen me sleep, tell me, was it 10 or 15 times that I've woken up? Then the colleagues must be silent and cannot tell her anything. Then you have this property. And now you can show the following. If you have a situation like that, and these loops have non-zero probability, then this predictivity enforces that what B calls her external world is contextual in the sense of Rob Speckens, where what's contextuality? You have an operational state, which are just her degrees of belief on the future given the present. The ontological model is just this computational process that she uses to predict the future. What's the ontic state? It's the state of this computation. What's the context? It's the number of times she looped. So you can show that this cannot be modeled within one joint probability distribution. That's something that we see in quantum theory. What about non-locality and no signaling? Well, it fits there too, but I don't want to go into detail. I just would like to invite you to look at interesting things that can happen if this looping is somehow correlated with distant random variables. You have a situation like that, where Abby does part of a Bell experiment within a locally realistic world where things can travel with finite speed, but then she sometimes loops back into her old state in a way that's correlated with a distant random variable, and can show this way, she sees a post-selected distribution that's non-local, and actually also no signaling. But I don't have really time to talk about that. And I'm not saying this is really how it works. I'm just saying it's not inconsistent with what I've tried to show you. Okay, so let's see if I'm actually out of time. Maybe 5 more minutes or something.
Yeah, 10 minutes of discussion.
And okay, so what would you get as kind of novel prediction if you take that seriously? I mean, you can say that's very strange. I don't take it seriously, which is fine. But if you do, then you get also some quite surprising effects. And one of them is that, as I've shown you, this objectivity is in some sense only an emergent notion, which is true asymptotically after you do many observations. So this means that there are situations where it does not apply. And these situations would be something like this, where you might have something that's really fun, that we call a zombie, probabilistic zombie. So what is a probabilistic zombie? It's basically something we've already seen on Renato's slides, more or less. So here we have B, so sorry for stealing your picture, B in his world, who sees the sunrise every day and who sees Abby seeing the sunrise with probability 1. But nevertheless, Abby does not see the sunrise with probability 1, but probably less than 1. And if that happens, then you might call B, A is somehow a probabilistic zombie for B. Yeah? I don't know if it's a good name, I thought it's a fun name. Yeah? But somehow the probabilities don't fit together. So this is some notion of inconsistency, maybe in Renato's sense. And you can actually write down a condition when to expect that to happen. So here this would happen automatically if the complexity of whatever that observer remembers of her state, it's much less than the complexity of the distribution nu, which are the probabilistic physical laws of B's world as impacting on A. So somehow if she's too simple in the sense of Kolmogorov complexity, then there will be no agreement between the two on probabilities in the future. Maybe something like that. Maybe this is not a good picture of a zombie in that sense. Maybe this worm with only 300 neurons, if you encode the content into some string, this complexity would be small enough to satisfy this inequality. Then 2 things, and too embarrassed to say much about them, so I just put up 2 funny pictures. One is about simulation, brain emulation. So in the beginning, I told you that there's a similarity between the Boltzmann brain problem and brain simulation. And now we've said something about the Boltzmann brain problem. I've tried to argue that it goes away if you take the postulate seriously. And so I shouldn't be surprised that we can also say something about these situations where we have a poor guy that we simulate on our computer. And we can say a bit like, how should we do that or not do that so that this, in fact, impacts the first-person perspective of some observer. And then you can actually look at situations like that and ask what happens if in A world something really bad happens to B, and you get quite interesting things that happen here that you wouldn't normally expect. But let me not say much about this. Instead, let me conclude. So hopefully I have convinced you that in principle, yes, we can start with the first-person perspective and obtain a notion of emergent external world consistent with known physics. I tried also to convince you that this allows to address some problems which are traditionally not considered to be in the realm of applicability of physics. Like why is there a world at all? What about the Boltzmann brain problem and so on? Now again, I want to emphasize it's just a proof of principle. It's probably wrong. And probably the world is not like that. Also, it has these open problems here. But it shows that in principle you can do it and you can try to learn something from that, what you would expect from such a theory. Basically, if there's a grain of truth to it, then the world would typically pretty much look as we think it is. But it would fundamentally, I think, be mind-bogglingly different. And I hope there will be something on the archive at some point if the moderators allow me to put it online there. Okay, thank you for your patience.
Hans Briegel, number 1. Markus, number 2.
So I was wondering about this notion of universal artificial intelligence that you were explaining to us. Because there are, if you understand artificial intelligence in an interactive way, as I have described it, learning from history and so on, then there are mathematical theorems called no-free lunch theorems. I'm not sure you are aware of. Which says that there is in fact nothing like a whole agent that can universally deal with all kind of environments and be close to optimal.
Yes.
Whenever this is this relative definition relative to an environment. You come up with some algorithm that can solve a problem that is a task that is given in that environment. Then if you replace the environment with something else, then it's a bad agent. Even the ordering of agents is different.
Yes.
So I thought there is that's really the basic problem of AI, that there's nothing like a Turing machine, like a universal agent that you can prove can deal with all kinds of situations. So what is this notion, or is there, in what sense is there the genuine AI problems of learning how to deal with new situations in all kinds of situations?
Yes. So it doesn't in that sense contradict Solomonov induction, what Solomonov did. Because Solomonov, all he said was, I'm only looking at the task of predicting what I see next, not agency. And only in those situations where I'm guaranteed to have an environment that's probabilistic, but the distribution is computable. So there is an algorithm that computes the distribution. And now these are already restrictions. So your environment might just not be of that form. And also the way it's phrased here, I mean, he would say, well, take algorithmic probability to make your bet. But algorithmic probability is not computable. So it's very difficult to really, get your hand on it. What you would do in practice is then probably more try to estimate it and try to, get shortcuts. And these shortcuts would probably boil down to something like you've shown us. So it's a very abstract kind of gold standard of learning in some situations, in computable situations.
So, actually, I have two questions, but maybe they are similar. So the first is that the approach sounds as if the agents are, to a large extent, passive agents in the way that they make predictions, but they act on the work. And then, this is a question whether this is correct. Let's say, account of what you're saying. And then my second question is, if you have two agents and they're talking about, for example, the sun rising, then although they're both talking about the sun, I guess in the representation of the agents, this event looks very different because they see from different perspectives.
Yes.
So how do you kind of link these two, that this is really the same sun, basically?
Very good. Yeah. So your first question, I mean, you're correct. There is no notion of agency primitively built into that. But I think this is not in itself a problem, unless a matter of taste, how you want to build a theory. But even in quantum theory, for example, you can say, when I have a Bell experiment, you can either talk about agents that choose the settings, and maybe you want to talk about that because it's very colorful, that's what we really do in the lab maybe. Or you say, I just have random variables that are uncorrelated with everything except the future light cones, as you do in your papers. And it's just equivalent. And here I would say it's like the second kind of formulation. You have these random processes, and then you can talk about random variables that are uncorrelated with other random variables. And then you might want to do that to mathematically talk about agency in that sense. Yeah. Second, how do you link these things? So it's linked, let me just go back quickly in the following way, prediction 3 here. So here's how to formally do that. So first you have A, and A's predictions are well described by this computation. And then you have a computable function that just reads out part of it. That's the way to formalize it. And the picture again is that you would say, well, that somehow you can think of really scanning what's going on there, encoding that into zeros and ones. So, and if you do that now and one moment later, you get a sequence of strings, and you can ask about their distribution, and that's what I call mu here. That's formally how you get this distribution mu. That's a formal answer, not operational one. I would not know how to do that if I were Abby.
So
I hope the question is not too naive, but I wonder if you can say something about, a comparison between what you do and other strategy to somehow derive intersubjective agreement on subjective probabilities, like typically those based on definitive theorem. I'm not an expert, so maybe the question is totally misplaced, but I'm very interested in this idea to somehow derive intersubjective agreement.
Yes. Very good question, in fact. So I think that some of what you use here, so you can interpret that stuff in different ways, and maybe you want to take a more Bayesian point of view. You want to interpret these probabilities in a Bayesian way and say, I don't assume that's fundamental, it's just beliefs on some world that's actually out there. And then these theorems, like this one, would basically boil down to Bayesian coherence. So we have two observers, and they make for a while compatible observations, and then the posteriors converge to each other. So I think it's related to this Bayesian coherence idea. That I think, maybe that's the best answer to your question.
So we have your second prediction that somehow simple processes are favored, or simple condition probabilities are more typical. I'm just curious to see how this relates to this observation that we think the world is simple because that's what we can apprehend. We would not be able to process complex. If the theory was very complex, we would not be able to synthesize it.
Yeah.
So, yes.
Okay, so you could always just disregard what I said and ask, well, why is our world computable? Well, maybe just because we built, evolution supplied us with tools to predict the future, and we call these tools computation, so we should not be surprised that the world in this sense is computable, because otherwise it just wouldn't work. We would be wiped out, and that's roughly what he said. And I would say, yes, one could try to make this argument, but the problem of this argument, I would say, is that you can always think of slightly different worlds that were until now exactly as we've seen, and then maybe in 1 year from now just become vastly more complicated. Or just sometimes, on Earth we can kind of make our way, but sometimes there are very strange things happening on Moon, things materializing, dematerializing in random ways. That would also be consistent with our survival, but it would not be something simple and compressible. So that's why I think that arguments like that will not get rid of the puzzle why our world is computable in some sense.
But in order to derive them, you need this assumption of typicality. So in what sense this is not circular?
Okay, we should maybe talk about this, because obviously what you call simple or not is always a bit difficult. Here you have homograph complexity, but then when you use it in everyday life and you really look at the laws of nature in your book, are they simple or not? How simple are they? It's hard to quantify, and maybe our measure of simplicity is already biased by what we can do or something like this. So I don't have a good answer to this question. But, yeah.
If you have basically an uncomputable universe, you can estimate what, even then would we see some kind of easy computable laws?
So, in some cases I think yes. So if you look in Hutter's book, the one I mentioned, then he says, well, so our machines now will do well in computable environments. What about non-computable environments? And then he gives a class of non-computable environments where the machines would also do pretty well in predicting what they see. Because maybe sometimes the way that you assign probability 1/2 to a bit is just because it's determined by some non-computable process that you cannot track. And so it's good enough for your survival to just assign probability 1/2. So I think in some cases the answer will be yes, but I don't really know much about that research.
There's no methods to handle it.
I think there's some research on that. I don't know what the status really is of that.